And here we have the dam for this, and water flows here and rotate the turbine. We connect the turbine with the generator, and as a result, we obtain the voltage and consequently the power. And this is the schematic, and this is the real photo. I have been in Żarnowiec 2 years ago, and I invited one of the power station in Żarnowiec. And this is the photo from the this part, from the highest part. And so this is the lower lake, and I stay close the highest lake, and we have here the 4 pipes which transmit the water from this lake to this lake. Okay, and this is the room when we can see the generators. This room and our whole building is located here near the lower lake, and this in this room we can see 4 generators. Of course, it is only the part of generators because the whole generators is below the floor, and this is not only generators, because it is the generators and the pump. Why? Because it is this power station has 2 functions. Firstly, of course, produce the energy, and the secondly, collect the energy. For example, when we don't, in our houses, we don't use many energy, they accumulate the energy, and this accumulation is in water. So when it is the more power in the power network, they pump water from lower to the higher lake. Okay, and this is the control room, and at this schematic we can see this higher and this lower lake, and this is the level of the water in this indicator, and the same in this system. And this is the control for all generators, and very similar schematic we can see here. And when we produce the energy, we transmit the power by the transmission line. I think that all of you see that transmission line. Okay, so now I would like to say about the advantages of 3-phase system over single-phase system. Firstly, we can use thinner conductors to transmit the same power, so we can reduce the amount of copper. And second, the lighter lines are easy to install and supporting structures. And very important that 3-phase equipment and motors have preferring running and starting characteristics compared to one single-phase system because of more even flow of power. Flow of power means that when you use the single phase, there is the big differences between the flows of power. It is the sinusoidal, of course, sinusoidal and square. So we have the moments where the power is very low and very high, and with pulsation. And this pulsation is here is the levels. The range of pulsation in power in this case is lower, so it is the better efficiency for transmit the power. And in general, most larger motors are three-phase because they are essentially self-starting. So they do not require special design for additional starting. For example, when we use the single-phase engine, we need to use special design. For example, there is the most simple design consists one condensator for shift the phase, and we can use also the another coil because without the electric motor cannot start. So I think about not the electric motor such we can make, and for example in the vacuum cleaner, because it is another kind of motor with brushes, but without brushes and cage. I mean about the motors with the cage. This is the cage motors. This name without the brushes. So this is the big machine about the 1 and more kilowatts power. Okay, so now we can focus about to frequency and number of phases. So the generated frequency is determined by number of poles. So it is depends how many poles, how many coils we put on the rotor, and it is also a function of shaft speed. You know about the frequency in power network in Europe. It is the 50 hertz. Of course, in USA we have the 60 hertz, but the values of frequency were chosen primarily because they can be generated by relatively efficient and stable mechanisms. So this is the optimal frequency from, for example, firstly from synchronization point of view, because you know we don't have one power station in the country, but in the country we have the several power station. We have, for example, household too with solar panels, and they also produce the energy and gives energy to another people. So there's the problem with synchronization, and when we increase the frequency, this problem is bigger. But for example, in ships, on airplanes, we can use higher frequency. For example, in that places there's a frequency about 400 hertz. And the second reason is that for this frequency we have the such device like transformers with low losses. So it is the good value of frequency. And another is that when you increase the frequency, so the shaft speed should be higher. So of course you can imagine that when we want to produce the more power, this machine is not small. It is the big machine with massive and mass, and there is the problem. So with the mass, and it cannot rotate with high speed. So it is the a solution for this by increase the number of poles on the rotor. Okay, so we have the number of and the frequency, and the three-phase system is used almost by commercial electrical generators. Of course, as I said, the number is not limited to 3. The first three-phase system was presented in 1889. It consisted of three-phase base devices as, of course, generator and transformer. So you can see this transformer, for example of transformer here, and engine as a load to present this system. Okay, so now we can focus on three-phase generator. Okay, and in the three-phase generator we have, you can imagine as the 3 coils placed with 120 degrees apart of stator, and coils. It is the good idea when coils have equal number of turns. So the voltage and induced across each coil has the same peak value, shape, and frequency. Okay. And this is the photo of such a generator, and this is the shaft, and we have the three phase and another one wire. Okay, and the real photo for this system. Okay, and this is the schematic for this system. So we have here the three coils and connectors respectively A, B, and C, and another, and it is the N connector. Okay, and for each coil we can write the equation with as a time function. So we have the magnitude and the sinus function for each of this phase, but for this one we have the phase equal 0 degrees, and here is the minus 120 degrees and plus 120 degrees. Okay, it is the important information, but at any instant of time, the algebraic sum of the three-phase voltage on a three-phase generator is equal 0. And I show you this picture. It is the simulation which I made in PSpice, and so we have three generators here. Maybe I switch for this program, and so we have the first voltage source. So I put here the frequency, amplitude, and the phase. For this phase is equal 0, and for the second, as we can see, it is the minus 120, and for the last one, this the same value but with plus. Okay, and this is the result of this presentation. And when we summarize this value, at any moment we obtain the 0 volt. Okay, and this is the same equations, and now we can calculate the RMS value for each phase. And this is the similar photo. picture to previous, but we have here instead of time we have pulsation here, and is in this picture we also see that any time the sum is equal 0. Okay, and of course it is the good idea for sinusoidal using the phasors. So we can represent this voltage as on the phasors plane. So this is the first phasor, the second, and the last one. I see the on chat the questions why there is the not two-phase system device. Of course, maybe I mentioned about it. Sometimes we use two-phase. For example, when you want to use the heater, the cook for cook the water. Or something like, for example, inductor plate, we can use for this equipment Y-phase power on two-phase or also three-phase, and this is the typical the device for cooking is typical device in our houses when we use the three-phase. I mean about the quite new flats and houses, because in old houses, not all old houses we have three-phase. For example, we have only the one phase and neutral. But when we use this device on one phase, the load is very high because for one phase. So it is possible sometimes using the two-phase system, but I think later I see why it is why we use the three-phase system because 4 is too more, but it's 2 is not enough for us from this point of view. Okay, so now I write another notation. This is the notation for exponential type of complex number when we have the magnitude and the phase. Sometimes we instead of e up to j, we use just the angle symbol. So it is the same. Okay. And also, when we add three phasors, we obtain the zero voltage because we start and end at the same point. So when we use the complex number, we obtain the same value equal 0. So now we are focused on Y connected generators. So you can imagine that the three terminals, which is the node N, are connected together. So this N we call the neutral point. So we had the two types connections in generator. First, the N point N is not connected to the load, so we have the Y connected three-phase, three-wire generator, and the second option is neutral Y is connected to the load, so we have three-phase, four-wire generator, and this is the generator. So this differences between previously that we connect together N, and we have the three lines A, B, and C, and neutral line which is not always. So it is the dashed line system. So some words. Lines, the three conductors connected from A, B, and C to the load. And for Y-connected system, line current, it is important for this system that line current, this is the current which flow by this line, is equal to the phase current for each phase. So the line current we write as with the later R, and phase with the phi, and G is connected with the generator. G like generator. R, small r as a load. Okay. So the most important, information. The next important information, the voltage between two lines, for example, A and B, or A and C, or C and B, is called line voltage. And now we can calculate the line voltage. For example, EAB phasor, which was drawn from the end of the B phase and to the phase A in counterclock direction. Okay, and now we can calculate the value of EAB. So we use this triangle, and we can you can write for this triangle EAB minus EAN, because it is the opposite direction, plus EBN is equal 0. So instead of BN, we can write ENB. So we should change the sign. And so we have this phasor here, E and B. So we have here this phasor, and from this picture we can calculate the angle between. So we know angle between this phasor and this phasor, and from this triangle we can calculate the half length of this phasor. So at the end we obtain that this phasor EAB has the value EAN, which is the phase value, multiplication by square root of 3. So this voltage is 1.73 times more than the phase voltage. Okay, and instead of this picture, we can use also the complex number for calculations, and I present now this method. So the first phase we have first, second, and second phase, EAN and EBN. So now we can subtract EBN from the EAN, and so this value is the same. This magnitude is the same, but of course the complex number is not the same because it is the differences in the phase. So here we have the phase equal 0, and here we have the phase minus 120 degrees. So now we change this exponential type of complex number to the trigonometrical, and after after some calculations, we calculate just this one and this one. And on the result, we obtain this factor, this magnitude, and such number. So this number now I call the x. So now I try to calculate the angle from this. So I have the imagine part and real part. When I calculate the arc angles from this, I obtain this value. So I obtain the 30 degrees, and the value of this the length of this vector I calculate from this. Okay, the ABS value. So as a result, we obtain this factor, the square root of 3, and this angle for this one and for another face also. So we obtain the same value. So it is the important information is that the magnitude of line voltage of Y-connected generator is square root of 3 times more than the phase voltage. And in the sinusoidal notation, I can write this voltage in the sinusoidal notation for each of line voltage. And here I have the voltage, phase voltage A and B, and this is the line voltage. In this case, it is the EAB. Of course, we can write it as a phasors on this plane. You remember this one previously, and so the another phasors connected with different phase are here. So this is the EBC and ECCA line voltage. Okay, and there is the same rule for this. The sum of the line voltage is also equal 0. So we can see at this picture it is the so I here I give you here this 3 voltage in the time, and this is the zero voltage. It is simply obtain this in this simulator. Maybe I show you because it is difficult for the line voltage, and for the phase voltage it is quite simple. So now I can switch on the presentation, the simulation, and I have the three signals, 3 voltage connected with 3 phase. And so now I can add a new plot, and I just add the first phase to the second and to the last one, and as a result I obtain this magenta line. Okay, I can delete another phase. Okay, and I obtain just close to 0. Of course, in practice, it is the 0 because it is the digital error for calculations. Only this. Okay, so now about this one, and so we turn to this presentation. Okay, and so now maybe after this it is clear why we use the 3, not 2 or 4 phases system. Okay, so phase sequence, another important topic. So the phase sequence can be determined by the order in which the phasor representing the phase voltage passes through a fixed point on the phasor diagram. the phasors are rotated in counterclockwise direction. It seems strange, but it is very, very simple. So we have the plane with the three phasors, and so we have the fixed point here, and this system of phasors, these three phasors, we start to rotate. So firstly, the phase A meets the point P. Secondly, the B, and at the end the C meet the point P. So we have the phase sequence A, B, and C. So we can interchange the two phases, and in this case, here we have the phasor C, and here is the B. So in this case, the phase sequence is A, C, and B. So phase A is a reference. So okay, so we have here the reference, we have some calculation, but when you see the plug in your house, or three-phase plug, and or something like this, or three-phase line, it is not we haven't not information. This is the A phase, this is the B phase, and this is the C phase, because it is not important. We, of course, in this picture and the previously, it is the static situation, but of course it is always change, because it is the voltage change in the time. So also the phase is change. Yes. So for us, it's not important which phase is A, B, and C, but for us it's important phase sequence. Okay, because I explain in the moment. So the phase sequence is important in the distribution in power. For example, it is the most commonly used three-phase motor is two-phase voltage are interchanged, the sequence will change, and the direction of rotation of the motor will be reversed. Okay, and now is we have two lines, for example, A, B, and C, and this is the coils in our motor. So, for example, when we connect this phase like this, this motor connected to these lines like in this picture, the rotation is in one direction. So when we want to change the direction of the motor, we can change two phases, interchange two phases. For example, A and B, or A and C, or C and B. It is not important which one we use. So it is in practice, if we have motor and we cannot guess it will be rotate in the right or left direction, and we cannot we have only three cables, and we cannot guess. So in practice we should use the phase sequence indicator. But how it works, of course, we will see later. Of course, you can imagine that in this indicator we have the small three-phase motor, and we observe the direction. It is also possible, but it is there is the simple method for this. Okay, so now we consider the Y-connected generator with Y-connected load. Loads connected to three-phase supplies are two types, Y and delta. And when we describe the Y-connected load to Y-connected generator, this system we can symbolically represent by Y, Y, and Y. Okay, and this is this system. So here we have the generator, two-phase generator, and here we have the load. Of course, the lines between generator and the load is length, is very length, but of course in this picture no. And so we have here the voltage, phase voltage, phase and phase voltage connected with the generator, connected with the load with index phi. And here we have the voltage, line voltage between any two phases. Okay, and another important information is, it is important information from test point of view. What is the balance load? Balance load is when we have the same impedance connected to each phase. So it is the important information. Maybe I change this. So it is the very important. What is the balance load? Okay, so we have the same impedance. So it is very important. Not the same resistance or capacitance, only resistance, but impedance. So we have the same resistance and the same reactance in each phase. Okay, and another important information is that for the neutral wire, we don't need the wire N. For balance load, we don't need the neutral wire N. It can be removed without any effective to the circuit. Okay. In practice, of course, many high power loads are balanced, so they not require N wire. For example, the big engine of required conductors can be solved, the required conductors can be reduced, but the most electrical equipment, for example, bulb on in our room, use only one of the phase voltage. So there is the never perfect continuous balancing all time because of equipment turn on off. So the neutral wire is necessary to carry the resulting current back to the Y-connected connected generator. So there is the reason why we use the neutral line from power station to our houses. Because locally we cannot use the N, for example, when we use the balance device. Okay, and for Y-wave system, we have the equation that the phase current is equal line current. It is equal the load phase current. For a balanced or unbalanced load, since the generator have and load have a common neutral point, we have the same voltage. And we know about this. The line is root of square root of 3 times more than the phase voltage. Okay, so now I give you the short example. So we have the three-phase sequence of the Y connected generator, and we know about the sequence is AB and C. So we know about this generator, and find the phase first. We want to find the phase angles phi B and phi C, find the magnitude of line voltage, and find the line currents, and verify that since the load is balanced, the current which flow in this neutral is equal 0. So we can remove this. So for calculation, we can assume the frequency is equal 50 Hertz. And so annotation for the first one, because we know the sequence, we can just write about the phase A, B, and C from this phasor diagram. Okay, and the same we can use for magnitude of the voltage. We know that in this configuration, Y configuration generator, we know that the voltage line is square root of 3 more than the phase voltage. So for the voltage 230 degrees, we obtain phase voltage. We obtain the voltage between any two lines close to 400 volts. Okay, and now we can calculate the line currents. So in this case, the line currents and the phase load current, it is the same because it is in line, it is the series connection. So now because we haven't any losses in this line, so the voltage at the load it is the same to voltage at the generated voltage. So we write this information here, and we calculate just the current. For example, this current we can calculate as a voltage across this load divided by the value of this load. And now we try to find the impedance. We know about the resistance. The resistance its value is here, and we know the capacitance. We know the frequency, so we calculate the reactance, capacitive reactance. So we know the whole impedance for each line. And now we can calculate separately each current. So the first, the second, and the last one. And now please notice that the magnitude is in this case it is the same. The differences are only in the phases. Okay, so and the last one, so we calculate the C, and now we verify this equations. So we just add any currents. So we apply the Kirchhoff's current law. We obtain the current which is in the neutral. It is the sum of A, B, and C currents. So when we add this one, and this one, we obtain the 0 amperes. So IN is equal 0 as we expected for a balanced load. Okay, so it is the good for balanced load, but maybe if I wrap it, I show you this current. So in this simulation, it is not possible to in the PSpice measure the currents directly in the line because the current is connected with the device. So I put here this very small resistance. This is the resistance, for example, one femto-ohm. This femto is such small that this is not any influence to this system. And I put here the markers to measure the current because it is not possible, as you can see. Yeah. So this it is only possible to measure here. Okay, so we have the balanced load because we have the same resistance. Maybe I put here the capacitors because it is similar to our presentation, but maybe we use exactly the same value from presentation. I don't remember. Okay, and so we have here this value, and so and now I try connect resistance and capacitors, and for B phase and for the last phase, and change the value of capacitors. We use the 7 microfarads. This one. The last one. Instead of later me, we should use the letter U. Okay, and it's not important, it's letter F. Okay, and so now write this simulation. Okay, so here we see the voltage, and now it is the current. So the current is equal 0 ampere because we have the balanced load. And now I try to unbalanced. For example, I change this resistance. So I change to, for example, less than 30 ohms, and now make this simulation again. Maybe it's not new. So okay, and we move the voltage of this, and you see that the current here is not equal 0, and it is on the same situation we should obtain when we change not only the resistance, but for example the capacitors. For example, I put here another capacitors and make the simulation. Okay, and in the result we obtain not 0 value of the current. Okay, so turn to the presentation. Okay, so you know that if we have the balanced load, the IN current is equal 0. Okay, so another configuration is when we have the delta connected load. So we have here the same generator, type of generator, and the delta connected load. Okay, so now for the balanced load, it is the same equations. The voltage across each phase of the load is equal to the line voltage. So the phase voltage here connected with the load is equal to the line voltage because we put the load between two lines. Okay, and for balanced load, the relationship between currents it is similar to relationship between voltage in previous system. So the line current is connected by this factor with the phase current, which is flowed by part of load. And three-phase, another example, three-phase sequence. We have the three-phase generator with the sequence A, B, and C. Now we can try to find the phase angles, find the current each in phase, and find the magnitude of line current. So, firstly, we find the phase. To find the phase, of course we can subtract the voltage, because we try to find the voltage between any two lines. As a result, we obtain this known value and phase. And now we know about that voltage across the load. It is equal to the line value, and now we can calculate. This is the same impedance in the previous example, and we now calculate the current. Of course, in this system, we cannot use the neutral wire, because we cannot connect to anyone. Okay, so now we can calculate the magnitude of line current. So it is this current multiplied by this factor, and we also calculate the line current. So use the Kirchhoff law. So we know about this current, and when we subtract from this current, we obtain this line current. Okay, and also it is possible to arrange the coil into the three-phase, use the three-wire alternating current generator. But from our point of view, it is not not important how it's connected with the generator in power station. Of course, when we connect, when we use these connections, we cannot. We haven't here the neutral line, but the neutral line you can also add after the transformer. So this it is not that system. And from this is true that we have the voltage line the same to the phase generating line. Okay. And so I see another questions. Will the presentation be available? Of course. So after this lecture, I give you by email the link for my Dropbox when I put this presentation, and also I put the some glossary for connected with this topic. Okay. Okay, so in this system, only one voltage magnitude is available. The line current for the delta connector system is not equal to the phase current, and the relationship to the two can be found applying the Kirchhoff current law. Okay, so maybe I omit it. Now we focus to the power. Maybe you see the wattmeter in your life, and so this in my high school I use such wattmeter. It's very big device and heavy device, and instead is this is the very simple construction, because so we know about the equations connected with the power. So when we want to calculate the average power, which we note as P, we must multiply voltage across the load and the current, which is flow by this load, and cosinus phi. So cosinus phi is the difference between phase voltage and current's phase. So in this power meter, we have the two coil. This is the current coil and voltage coil. So the interaction between this magnetic field and this magnetic field give us a result, show the power of this load. So we should separately set the range of current and the range of voltage, and it is also it is important the beginnings of these connectors. The beginnings is with this asterisk, because when we connect when we reverse reverse this is we obtain the below zero, and we can destroy these systems. Okay, but in our times it is less complicated system. For example, the digital panel meter, and some connections between digital and analog display. Okay, so the average power delivered to each phase we can just calculate as a voltage on this load in one phase, and current, which is flow, and cosinus phi. Because the cosinus is connected only with the resistance, we just calculate the average power as a current multiplied by this resistance. Okay, so the total delivered power, but only for the balance load. So we have the same Z here, and here. The total power is 3 power of for one phase, and P total can be calculate. Also use the line and line voltage and current in the line. Okay, and the same we can make for the reactive power, but the power average power is always more than zero. And in opposite, the active power of each phase, which can measure which in var, can be more than zero for lagging load, or less than zero for C leading load. And this is the equations for this type of power. Instead of cosinus, we have here the sinus. So sinus is connected not with the resistance but with the reactance, and also very similar equations for total power. And we have, because we have the three types of power, the apparent power of each phase, we can calculate as multiplication voltage and the current. So the total also is the 3 for one phase. But it is all this is all only for the balance load. You must remember. At the power factor, we can calculate the power factor as a ratio, the average power to the apparent power. And we obtain leading or lagging system. Okay, so when we have the delta connected balance load, we obtain very similar equations. So maybe I omit it, and the same the power factor. But here we have another value of voltage, because when we have the same load, the voltage instead of phase voltage is equal the line voltage. So we have the line voltage, which is larger than which is higher than phase voltage. So the power is also larger. But I see you later. So now we compare the power in Y and delta connections for the same load. So we have here the load Y connected, and we know about the voltage and the power for one phase. And for delta connections, as I said at the moment, we have the voltage with this factor. And of course, when we powered this factor, we obtain the very important result. Very important result that for the same load connected with the delta, we obtain 3 times more power that the connected with the Y connected. So in other words, when we have the one engine, when we connect in delta, we obtain the 3 times more power on the shaft of this engine. Okay. Okay. So it is used in practice. So this is the box connected with the engine, electrical motors, and so we have the inside we have the three coils, and this is the connectors: the coil 1, coil 2, and coil third coil. And when you want use the the Y connected, we connect these ends together, and we connect here the power, first, second, and third phase. And here is it is for delta connections. We of course we not connect the same coil. We not short the same coil. You know that this is the another. This is the W2, and here we have the U1. Not W1, because it's not good idea to short this. And okay, so in practice you can make such switcher. This switcher is for soft start of engine, because when the engine is stopped, the current at the moment when we connect, it is very high. So firstly, we shift from 0 to Y connection, and when the engine is start, we change to the delta when we want to use this engine in more power, for more power application. Okay, and this is the example. And in this example, find the total average reactive and apparent power, and find the power factor load. Okay, so we have a very complicated load, first only, but we can divide it into two parts. Here we have the delta load, and here we have the y load. Okay, so consider the delta and the delta. We know about the resistance and the impedance. We can calculate this, and we know about for the delta we have here the voltage equal 200 volts. So we can calculate the magnitude of the current, and when we have the magnitude of the current, we can calculate the average reactive and apparent power in this system. Please notice that here we have the minus, because it is the capacitance reactive. And for this type of the load for Y, we can calculate in the same way and obtain the another value. And at the end, for the total load, we just summarize the first to with the second, and result as a result we obtain the total average operative and reactive power, and total power factor connected with this whole load. Okay, and the next question is how we can measure the power to multi-phase system. Okay, so we can just use the for balanced or unbalanced load, we just use the 3 wattmeter, and this is the current coil and voltage coil for each wattmeter. And total power, it is just the P1 plus P2 and P3. And when we have the delta load, so we have here the first, the second, and the third wattmeter, and it is the same equation. So in any case, we must cut the line and put here the voltage coil. Okay. And for balanced Y or delta load, the power delivered to each phase is the same. So this is this and this is true. This equation and this equation is true for any type of the load. But when we have information that we have the same load here, so we have the balanced load. We cannot use we cannot use 3 wattmeter. It's only 1 and multiply it by 3. Okay, and we have also another configuration, so we can also measure the power for any type of the load. Iron configuration. In the Iron configuration, we use the 2 wattmeter. One end of each potential coil is connected to the same line. So the current coils are placed in the remaining lines, like as this picture. Okay, and for this system, we can write from power's triangle that the apparent power is the P plus JQ, and because you know the P, it is the V, I, and cosinus, and Q is the VI sinus. So we can arrange this, and instead of trigonometrical form of complex number, we use the exponential form. And of course, we know from the previous pictures that what is the phi. And now, instead of this phi, we use this. So as a result, we obtain that the equations that the apparent power is equal complex voltage multiplied by conjugate number of complex I. So in the two-phase system, we know that this is the we can summarize this power as this power, and so I write this for each one. But we know that the current is the sum of this current from the Kirchhoff law is equal to 0. So now we can express this current from these equations. And after some calculations, we obtain that the operative power is the P plus JQ, and this is the important that is this voltage and this voltage. So in this configuration, wattmeter used not the phase voltage but the line voltage, and 2 wattmeters is enough for measure. Okay, and so because the P is the real part of S, so of course the wattmeter measure only this, not Q, and we have just the total power is the P1 plus readings plus P2. So the total power delivered to the load is the algebraic sum of the 2 wattmeter readings. It is very important that the algebraic sum, because it is sometimes the readings can be less than 0. So, and for the balanced load, when we have the balanced load, additional one is that we know the power factor of any phase of the load and the magnitude of the power. We can calculate the total power, or when we know about the total power, and this is the readings magnitude of lower and higher readings of wattmeter, we can calculate the power factor of whole system. And for the balanced load, it is possible to obtain the reactive power from these equations, but it is only true for balanced load. So using the ARM configuration, we can calculate the total average power, but when we know that the load is balanced, we also calculate the reactive and also calculate the angle, but only for the balanced load. So this exclamation mark is I put here that it is the important information. So in our lectures, when you meet this mark, it is the nearly 100% that this information is using will be using in the end on the test. Okay, and sometimes there is a problem with 3-wire systems to measure the power, because for example, you know that the load is balanced, and now when you want to measure the power, we need the neutral point. But in this this network, we haven't an line, so it is we can use the same resistance to make artificial neutral point. But we must be careful because this resistance and the value of this resistance, it should be the same to internal resistance of coil, voltage coil of wattmeter. Okay, and at the end, two slides about connected with unbalanced three-phase load. So unbalanced for polyphase system, none of the load impedance are equal. So we have such situations here. We have the Z1, Z2, and Z3. So of course we know about the current when we have here the voltage, for example, V1. We can calculate the current which is flowed by this load. But it is true for this on the Kirchhoff current law that the neutral current which is flowing this neutral line is the sum of another currents, phase currents. And in this system, because it is the Y, so in this system Y, the line current is the same to the phase current. Okay, so in the three-phase, three-wire, Y connected, not balanced load, we can write. Maybe it's a good idea in this picture. So we have here the voltage, for example, EBAB, and EAB minus this voltage and minus and plus this voltage is equal 0. So for this loop, I can write these equations, and similar equations for this loop and this loop. And we can range this value to obtain as a result, we obtain the current which is flow here, and here. Because I cannot use only, I calculate this current using the line value of voltage, because this line value of voltage is constant here. The phase value is not constant because I don't know about this value at this point, because this value of this point is the different, because we have not balanced systems. And in our present simulations, for example, we have here not balanced system, and maybe I omit this and this line and this current also. And now I just mark voltage here, and I have not this one. And now I'll show you the voltage here. Okay, it's just some errors. Not a good idea to use, because sometimes we cannot simulate. Maybe I omit here now, because it is a problem with this point, or it's because we have not any line. Maybe I give here the large resistance like 100 mega ohms. It's not here, and here. Right. Okay, so you can see that for unbalanced balanced load we haven't zero voltage. So when we here the balance load, we obtain the zero volts. So for unbalanced in this system, we don't know about the voltage. Okay, of course, when we have this equation, we can calculate, and the last one is because I promise you that I show you how is the phase sequence indicator is built. It is the construction. So we have it is very simple construction. This phase sequence indicator consists with the one capacitor Z1. So we have here Z1 and Z2 and Z3. It is just the resistance, and it is the resistance close to 1 kilohertz for 40 watts bulb. So instead of resistance, we just use here the two bulbs and simulate it as a resistance at this value. And from previously equations, we can calculate the voltage in this point. This is the N prime point, and in this system, when I put instead of Z1 and Z2 and Z3 respectively value, I obtain the value at this point. Okay, and now I can when I know about this voltage, and just calculate the current which is flow in this phase. It is the differences between VBN and Vn, and divide by Z2. And I calculate this current and this current. And so when we have the such sequence, this bulb is lighter than this one, and for this sequence, it is another situation. So this is the phase sequence indicator. Very simple, but it is a good idea. Use some this kind of sequence indicator. Of course, this capacitor is not the. It could be. It could be chosen to take to account the voltage across these capacitors. So it cannot be small capacitors. Okay, and so thank you for your attention. So this is at the end. We have here the cable. You can met this type of cable in your flat, in your houses. So you must remember that always the blue is the reserved for N, for neutral, and yellow with green, it is the PE cable, and the gray, brown, and black, or sometimes all three is black. It is the cables connected with the phase, and this is the typical plug for the three-phase line, and you know L1, 2, and 3. This is the neutral, and the most thing it is the for protections, and of course you can see that it is the length is the big it is the longest because when we disconnect this plug, so it disconnect at the end because of it is protect protect us. Okay, so thank you for attention, and after several minutes, I give you the link for Dropbox for these presentations. Okay, so thank you, bye.